All right, so in this video, I'm going to introduce the sinusoidal source and kind of just talk about, the sine function that we talked about in the previous video. We were talking about sine and cosine, but I'm just moving over to sine now. Probably going to stay here pretty permanently. And I'm going to include this. I've kind of expanded omega out to equal 2 pi f again. And let's just treat this as an example. And let's say I'm interested in determining what time this is, where 2 full cycles have been completed, right? I've got one cycle here and then another cycle here. So I want to know what time that occurs at, assuming that my frequency, f, is equal to, let's just say it's 250 kilohertz. Okay, right? So I'm saying that my frequency is 250 kilohertz, and so I want to know how long it takes for 2 cycles to occur. Well, I know how long it takes for 1 cycle to occur because my period is equal to 1 over my frequency. So I can find this t value right here and then just multiply it by 2. So let me go ahead and just say 1 over 250 kilohertz. Actually comes out to about 4 microseconds. So I'd be at 4 microseconds right here. And then this second value here would be 8 microseconds. Okay, and then the third cycle would complete at 12 microseconds and so on. Right, so my t value, which goes from about there to there, that is 1 period, right? That is 1 over my frequency. And so what is this Vm telling us? Well, that Vm is going to tell us the height of the sine wave. So if I were to zoom in on this plot, this peak value right here and this one are at a value of Vm. And this negative peak, or you can call it a trough if you want, that one is at a value of minus Vm. So whatever this value is here, that's my peak value of my sine wave, okay? So typically you'll see sinusoidal sources take this form. So you would see something like this, and you would see, maybe it would be called like Vs of t, and you'd see something like 3 times the sine of, in this case it would be 2 pi times 250 kilohertz times t. And so in that case, then my voltage Vm would be 3 volts. And this lower voltage here would be minus 3 volts. Okay, so this sine wave would be swinging between positive 3 and negative 3 volts, and it would complete a cycle every 4 microseconds. Okay, so that is what this expression here derives. It's telling me that this source, and it's going to produce a voltage, between these 2 points that behaves as such. So if I were to take this bottom node and ground it, then this waveform right here would show up at this positive terminal, similarly to how we saw it with the DC source, where if I had a DC source, and I say that I have a 5-volt source, then I know that that means I have 5 volts between my plus and my minus terminal. Well, it's the same thing with an AC source, where if I just ground the minus terminal, then I know that the whole 5 volts just shows up at this plus terminal. The case is the exact same for the AC source. If I ground the minus terminal, then the entire sinusoid shows up here, referenced to 0. However, if this wasn't 0, then again, all I know is that the difference between my plus and my minus terminal at any given point in time is equal to this function, right? So if I said that this was 6 volts, for some reason, let's say this node was tied to 6 volts, then that means that when this sinusoid or this source reaches its peak, the peak would actually be at 9 volts, because it would be basically this entire signal plus 6 volts, because I would have to take into account the fact that the difference between this point and this point has to be equal to my function at any given time. So when it's at its peak, I would need 9 minus 6 to get me this 3 when t is equal to 1 microsecond at that point, which would be 1/4 of a period. You can, work that out if you're interested in figuring out what I'm talking about there with the 1 microsecond. But I'm basically just saying that at the peak point, if I want the voltage across my source to be 3 volts, I would need this to be, to reach up to about 9 volts, assuming it's sitting on a 6-volt DC. But I don't want to get too far ahead of myself. I just want to make the point that if we ground this, then we can just, treat this node right here as if it behaves according to this function, similarly to how we did for a DC source, okay? So let's go ahead and end this video right here. And in the next video, I think I'm going to talk about amplitude. Again, this is called the amplitude right here, this VM that we were talking about. I'm going to talk about amplitude, frequency, and phase, and show what examples of each of those look like. Okay, so I'm going to go ahead and stop this video.